All right, so we are going to do a lab here on a titration. So for titration, the whole purpose is we're going to have something that we know what it is to try to figure out the concentration of something that we don't know what its concentration is. We know what the substances are, we just don't know what their concentrations are. And so we're going to start with a sodium hydroxide concentration, which you're going to write down in your lab is a 0.6. So there's a little spot right here for you to write on your lab paper 0.6. And you'll see that it says sodium hydroxide, and the original was hydrochloric acid, so I've switched the whole lab up. All right, so you've got the concentration of the sodium hydroxide, which we know, and we can't tell by looking which one is which. So how do we know? We're going to use an indicator. In this case, we're going to use the indicator phenolphthalein, and I want you to know some of these things for your test and or quiz. And here's a little bit of the anatomy or the parts of this whole setup. These things are called burettes. These parts here are called stopcocks. This is an Erlenmeyer flask, and this is what we're going to do our mixing in. Why? Because we can shake it and none of the fluids will fall out. If you take a beaker and shake it, why, the water will come out, or the solution will come out. We're going to use Erlenmeyer flask. All right, so first thing we have to do is to fill our burettes. So one of the safety things is we never fill above our heads because we don't want any spills to come down in our eyes. So we're going to go down here into the sink. I'm going to make sure I'm grabbing my sodium hydroxide, but I've labeled it that, but how do I know for sure? Well, I know I have an either or. It's hydrochloric acid or sulfuric acid or sodium hydroxide. So I'm going to do a quick little check here. I'm going to take some litmus paper, which is a indicator, and I'm going to see, does it turn it blue? If it turns it blue, then we know it is a base. So we've got it set up right. Now I'm going to pour it in here. I'm going to pour it. And your lab will talk about doing some rinsing and so forth. And in the interest of the video and time, I'm not going to take time to do the rinsing. But we're going to fill this up past the 0 point. Now, it may be a little strange. The top of the burette is labeled 0, and the bottom of the burette is labeled 50. And we're going to go a little above 0, as we just did there. And we're going to run it down a little bit as long as we go below 0 for our starting point. Oh, we happen to land right on 0. We'll take that. All right, and we've got this burette all nicely filled. And this one, we're going to use hydrochloric acid. Now, how could I check if this is hydrochloric acid? I could grab some litmus paper and see, oh, it stayed pink. It must be an acid. All right, let's pour this one in. Again, below your eyes. All right, we went above the 0 mark. Now I'm just going to run it down a little bit. And, oh, perfect, right at the 0. All right. So now we're ready to begin our titration. So our lab says to put about 10 milliliters of sodium hydroxide into our Erlenmeyer. So I read the curve of the meniscus. The bottom is where it starts. So we're going to start at 0, and we're going to go down about 10. And it just goes down. I know you can't quite see the numbers as well as I can. All right, doesn't have to be exactly 10, but about 10. All right, but we can't tell what's going on in here. So what we're going to do is we're going to get our indicator, and we're going to put just a couple of drops in here. And the nice thing about phenolphthalein is that it turns pink in the presence of a base. And so here we have some nice pink color. Our goal is to find out when it reaches equilibrium, and we have just exactly the right amount. pH, the endpoint for phenolphthalein is around 7, and so That's why we're going to use phenolphthalein. I'm going to add some water to rinse down anything on the edges. Now the important thing here is that I haven't changed how much is in there. I changed the concentration of what it was, but I still know how much is in here by our calculations. So what we're going to do now is we're going to add hydrochloric acid until it changes clear. So I'm going to go fast at first, but I'm going to be constantly agitating to see when it's going to change. And you can sometimes watch it start to change in the middle of the solution, and then you know you're getting kind of close. And our goal is to change it by 1 drop. All right, boy. Okay, so there we are. But we don't know if our equivalence yet. We're close. We're going to check. We got to get it to go back and forth by 1 drop. Again, I'm rinsing down the splashes so that we make sure. So here we are trying to get it to go. I'm going to be a little more careful now. I'm just doing it a little bit. If we can get it to stay pink, it only took a couple drops. All right, so we're going to go to the other side now. Again, a little rinse, and we're going to add, let me see if I can do it. Whoop, oh, too much. That's a popular thing to do. Well, it turned out to be not too much. Let's do a little bit. I'm just dropping it. And the white paper there helps us to see it's clear. We are almost there. All right, let's try it. See if I can get 1 drop here. See if it turns pink. Yeah. This is a patient process. We are just a hint of pink, so I'm going to do 1 more drop. All right, so you can see there's a faint little pink there. And we are going to now write down our data. So I want to show you where we stopped on our reading. I'm going to read at the bottom of the meniscus. And that's what you're going to put down for your end reading. Our initial was 0 for the sodium hydroxide, and our end reading is 10.3. 10.3 for our sodium hydroxide, and our hydrochloric acid started at 0, and we are ending at 14.7. 14.7. Okay? Now, instead of filling these back up again, we're going to just keep on going where we started, where we left off. So this is going to be our new initial, and this is going to be our new initial for our next trial. So you'll see on your paper it says trial 2. So your ending numbers here become your starting for trial 2. Why don't you go ahead and stop. For trial 2, we videoed in time lapse so that it went faster. And the data for trial 2 will follow here. Still good for you to watch the process in doing a titration. So for the sodium hydroxide, for our second trial, we ended at 20.4. I'm sorry, 20.6. And our hydrochloric acid, we ended at 29.4. 29.4. So this is trial 3 in a time lapse, and the data will follow the time lapse of trial 3. Our final reading on the sodium hydroxide is 30.2, and our final reading on the hydrochloric acid is 43.4. All right, that's your final reading for the data on the lab. All right, to finish up this lab, you're going to need to find your volume of each trial, and you're going to do that by taking your final volume minus your initial volume. And you show your calculations here and find all your volumes. Now I just wanted to walk you through one trial's calculations. Just a reminder, the concentration of the sodium hydroxide we knew to be 0.60 molar. Now, we need to know how many moles of sodium hydroxide we used to figure out how many would react in equivalence with the hydrochloric acid. So, to do that, we're going to take our volume from our first trial, which for sodium hydroxide 10.3 minus 0 is 10.3 milliliters. Well, molarity is in moles per liter, and this is in milliliters, so we need to convert this to 0.0103 liters. And this is going to be the beginning of our calculation for right here. So we're going to take the molarity, and it's going to go here as 0.60, and we're going to convert molarity, which is moles per liter, to just write it as moles of sodium hydroxide per 1 liter. And you see our liter units will cancel, and this turns out to be, you put it in your calculator, 0.00618 moles sodium hydroxide. That's how many moles were used. Now, you need to write a balanced chemical equation here. This is important because we want to know the mole ratio. In this case, the mole ratio is a 1-to-1 ratio. So, and I did mess this up. This is not base. This is acid. They had it messed up with both acid. This is acid. So acid. So to find out if I know the number of moles of the sodium hydroxide I used, this here is going to be the exact same number. So we're going to write here 0.00618. That'll be the exact same number. No calculation needed here. And you don't need to change that. But the last part requires a calculation. So how do we find the molarity of the hydrochloric acid? Well, molarity will be the number of moles divided by the volume. Well, since the moles of sodium hydroxide are the same as the hydrochloric acid, we're going to do 0.00618 moles of HCl, because those numbers are the same, because it's a 1-to-1 ratio. Then we're going to divide it by the volume from our trial. And on our trial, that's 14.7 minus 0. Well, with turning it to liters, that's 0.0147 liters. So this will be moles per liter. Put that in the calculator, and it comes out that we have 0.42 moles, or molarity of HCl. And that is our answer that goes right there. Now there's one last thing to calculate, and that's the average. Once you get all 3 trials calculated, you're going to add all 3 together, divide by 3, and get an answer for what the average is. And that's hopefully going to increase our accuracy. The last thing you need to do for the lab is to answer these 2 questions. It says you add distilled water to the solution. You saw me rinsing it to make sure that all the chemical went to the bottom and didn't get stuck on the sides. How come it didn't affect the results? Because since I added that after it went into the Erlenmeyer flask, it, while it diluted it, it's still based on what was in the burette. And so I didn't change how many were there. That's like asking how many people are in the room and then make the room bigger. that doesn't change how many people are still in the room. And then lastly, what is it about phenolphthalein that made it appropriate to use for this titration? Could you have done this experiment without it? How does phenolphthalein's endpoint relate to the equivalence point of the reaction? So first, what made it appropriate to use for this titration? Well, one is it changes color. And we couldn't have done it without it because we would not know when we have it, the acid and the base in equivalence. The endpoint is what helped make it appropriate for this because the endpoint of phenolphthalein, it just changes right between 7 and 8. And so the endpoint is close to where the chemicals are in equivalence when we have just as much sodium hydroxide as we have hydrochloric acid. And lastly, I want you to write down here what was made in the chemical reaction. And the answer to that is salt and water, which you could have drunk, or I could have drunk. I'll never do it because I'm always nervous that somehow I've messed things up and I don't want to drink hydrochloric acid or sodium hydroxide. But in concept, if you mix those two together, you've made salt and water, and that would be relatively safe to drink. Of course, it would dehydrate you a little bit, but it's not going to kill you. All right, that concludes our lab for today.